Hi, this is Jimmy the Rusty Pilot. Welcome to my channel. Let's get started. Today we're going to be going over weight and balance theory as it relates to aircraft. And basically, as the name implies, two very important things we have to know are the total weight of an aircraft, okay, and its center of gravity or balance. When we're talking about the total weight, basically you have to know the maximum takeoff weight and the maximum landing weight allowed, and that is determined by the manufacturer. And when we're talking about center of gravity or CG, you're talking about the balance of the airplane from nose to tail. We're not really so much concerned about in calculating weight and balance. It's the wingtip to wingtip, side to side. Okay, if you have too much fuel on the left, you can always transfer it to the right, depending on the type of aircraft, etc. Or you can move passengers left and right. Okay, but when we're talking about weight and the CG, we're talking nose to tail position and that balance. All right, so let's start with the theory. As we basically, I'm going to try to go ahead and draw a seesaw here as best I can. Okay, my lines are not coming out too straight. So let's say I have a seesaw. Here's my pivot point, which if you remember learning about levers in school, it's called the fulcrum. But since this is our balance right now, this is balance. The seesaw's balance, and we're going to call this our CG, or center of gravity. All right, so let's say we have a 100-pound ball on the left and a 100-pound ball equal distance from the CG on the right. We get this balance condition. Okay, same weight on the left as on the right. Okay, so that's very simple. Okay, nice and balanced, equal weight on both sides. Okay, but that's not typically what you're going to get in an aircraft. So now let's see what happens if I were to draw a similar type of seesaw, but now this time, okay, I have 500 pounds on the left. Okay, I have 500 pounds over here. 500, and on the right, I have the 100-pound ball. Okay, I don't know why I made them the same size, but 500 on the left, 100 on the right, and you notice obviously the left is going to go down, has more leverage, right? But we're no longer balanced. So in order to get this balance, what do we need to do? Well, this center of gravity position would have to shift to the left, and eventually it's going to keep shifting to the left, where we would get something like this, similar to this. Now we'd be balanced again. Okay, now the pivot point is more to the left. We'd have the 500-pound ball here. I'll make it bigger this time. And we'd have the 100-pound ball over here. Okay, our center of gravity shifted to the left. Okay, it shifted. It was here initially, and now it's over here. Okay, so airplanes, okay, when they are loaded, they have to be, even while it's flying, it has to be within what they call CG limits. And usually, let's say in a small Cessna, it's going to be somewhere under the wing. Usually, it's not more than 12 to 14 inches that center the limits, right? So you'll have limits. Like how far, where does that concentrate? That balance point has to be somewhere in here, probably. Okay, I don't know the exact, but close, somewhere near the wings. Okay, that's will be our pivot point, or we call our center of gravity. Okay, or our balance point. So that's what we're talking about. We're talking about balance along with the weight. So let's go ahead. So let me go ahead, and there's something called the law of the lever. All right. So let me just go ahead and give you some terminology when it comes to weight and balance. All right. So we already know the fulcrum right here. Well, if it's balanced, if this seesaw, we'll say this is a seesaw. If this is this lever, if it's balanced, we're going to say the fulcrum is the CG. Okay? Now, you notice we have two weights here. Okay, one to the left of the balance point of the CG, one to the right. Okay. The one, so we want to know what position where those balls, where they're located, the position. So we're going to say this line here, it just happens to be the datum, the word datum. Datum is a reference point. It's where you take your measurements from, right? So it's a reference. I'll put a ref like that. Okay. So right now, it just happens to be that the CG and the datum are located in the same place. So if we have, so the law of the levers basically says, okay, if we get a weight, okay, an object, let's say the one on the left, we have a 100-pound weight. I want to put W for weight, it's 100 pounds. And we multiply it times its arm. The arm is the distance from the datum, okay, which we arbitrarily chose, to its center of gravity, so right here, okay? Basically the middle of the ball, that's the center of gravity of the ball. That's called the arm. So if we get the weight and we multiply times that distance, which is usually in inches, in this case, it's to the left of the datum. And we're going to call the datum position 0. Anything to the left is negative, anything to the right is positive. So position negative 50, that's 50 inches to the left of the datum, which is, okay? And if we multiply the weight times arm, what we get is what's called the moment. And here you see it here, negative moment, we're going to need 100, type negative 50, we get negative 5,000 pound inches. All right, so now if we go to the right side, we have another weight, okay, this ball, it has a weight of 200 pounds. Its arm, if I put inches, its arm, or distance from the datum, here's the datum, from here to here, is plus 25 inches, positive, because remember to the right is positive, in this case right of the datum, 200 times 25, we're going to get positive 5,000. So what the law of the lever tells us is, when you calculate the moments on either side of the balance point or the CG, if you add them together and they give you 0, that it's balanced. Okay, so right at the 0 position, it's balanced. So it's negative 5,000 plus 5,000 equals 0. Okay, so that means this checks out. Okay. All right, so let's talk about a little bit about the datum. I think I said datum earlier. I think it's datum. Okay, the datum can be located anywhere. Okay, it's usually determined by the manufacturer. It could be, in this case, it looks like it's at the firewall. It could be at the leading edge of a wing. It could be here at the tip of the spinner. Sometimes some aircraft may even all have it way ahead of the aircraft somewhere, so a certain number of inches ahead. Okay, the datum's always, wherever it's at, it's always position 0. Okay, so generally when you're going towards the back of the aircraft, it's going to be positive. Towards the front, it's going to be negative. Okay, so let's see how. Let's see an aircraft that has its datum ahead of the aircraft somewhere, towards the front. So let's go ahead and I'm going to go ahead and give you an example here. So let's say now I'm going to have my datum out here. I'm going to have a datum, and there's going to be, so we know datum is going to be position 0. Okay. All right. So we're going to go ahead and do my little seesaw again as best as I can. All right. So I'm going to put my CG over here somewhere. All right. So now I have so we know the datum is position 0. Let's go to position 50. Okay, position 50. let's say it's position 50 is here somewhere. Let's say here, and we're going to have a 100-pound ball. 100. All right, and that's position 50. So from here to here, that's 50 inches. Okay, and notice it's positive because the datum is 0. Everything to the right is going to be positive. Then we're going to have another 100-pound ball, and we're going to call this one position, and we're going to call this one from the datum to the 100-pound ball. The second 100-pound, the red one's going to be position 90, which is, and we say positions how many inches from the datum. 90 inches, that's the arm for position 90. Okay, it's also positive because it's to the right of the datum. And then we're going to have, on the other side of the CG, we're going to have a 200-pound ball. Okay. And let's say this 200-pound ball, which looks like an 800-pound ball. And we're going to say that this one is position 150. Okay. 150. 150. Okay, we have position which is positive 150. That means the distance from the datum all the way to the center of gravity of this ball is position 150. All right. So now let's go ahead and work out the moments like we did before. So if I were to start doing the math, the first object, okay, the blue ball, is 100 times 50. So what do we have as our moment? Right, remember, weight times the arm is the moment. We get positive 5,000. Okay, pound inches. So I'm going to say positive 5,000. I'm going to add that to the red ball, which was position 90 times 100. And that gives me positive 9,000. So that's 9,000. Okay, and I'm going to add that to position 150. The arm of 150 times 200 pounds. 2 times, that comes out to 30,000 pound inches. That's the moment. Okay, so if we add these all up, and our total moment is 44,000 pound inches. Okay, and our total weight is, we have 4 balls, 100, 200, that's 400 pounds. So our total weight equals 400 pounds. Sorry about the comma, it's 400 pounds. Okay, so let me go ahead and go to the next slide. And there's the formula. We had our total moment, which we said was 44,000 pounds. We're going to divide that by our total weight. Here's our formula, 400. And we're going to get 2 zeros crossed out. I know that for sure. Okay, and then we're going to get 440 divided by 4. That's 110 inches. Okay, and just remember, this was pound inches, and this is pounds. The pounds cross out, cancel out, so you have inches. So our answer is 110 inches. That is the position, or the arm, right? Because total moment divided by total weight equals an arm, which is our CG, center of gravity. Okay? All right, so that's 110 inches is where our CG would be. All right, so if I were to go back to here to our drawing, this position here would be position 110 inches from the datum. Okay, all right, that's that's where our center of gravity is. Okay, all right. So now, how can we prove this? Well, I'm going to try to do my best. Well, to prove this, we need to, okay, I'm going to kind of redraw this how we had it before. Okay, I'm going to go ahead and put my, let's say my original one. Okay, our datum, we had it first at 0. We had our seesaw, correct? Okay, we had a 100-pound ball, another 100-pound ball, and we had, I think the other one was a 200-pound ball, but we had them at positions. So this is 100, 100, 200, and we had them at positions 50 inches, positions 90 inches, positions at 150 inches, all positive, right, because to the right of the datum. Now, if I were trying to redraw this at the bottom here, okay, same position, okay, I'll kind of redraw the seesaw here. Let's make our datum 0. Well, we're not changing the position of the balls. I'm just trying to prove what we just did. If we made our position 0 now, okay, well, we already know up here, this CG we calculate to be 110 inches. Okay, well, from 110 to 150, let's say the 200-pound ball is 40, 150 minus 110 is plus 40, so we go 140 to the right of the datum would be this position here. So that would be, okay, the 200-pound ball would be at position plus 40. From 110 to 90 is only 20. Left of the datum, this 100-pound ball is position minus 20, the 100-pound ball. And then from 50 to 90 is 40. So minus 20 to minus 40, this 100-pound ball will be position minus 60. And if I were to do the math really quick, okay, I would get 100 times negative 60, and it's negative 6,000. That's my moment. I'm going to add that. 100 times negative 20 is negative 2,000. Okay, there's the negative side of the moments. Okay, negative 6,000 plus negative 2,000 is negative 8,000. And look to the right of the CG. Remember, this is our CG. 200 times 40 is 8,000. Positive 8,000. We add them together, the moments, and we get 0. So this 110-inch CG checks out. Because remember the law of the lever. Okay, anything to the left is trying to bring the left side down. Anything because of gravity, right? Notice anything, the weight on the right is trying to bring that side down. Okay, and the law of the lever says if you have them, both moments are equal, okay, it's going to be balanced. Okay, so that is my little weight and balance theory. I hope you liked my explanation. Go ahead and give me a like if you liked it, subscribe, and if you would like me to answer any questions about weight and balance, go ahead and leave a comment, and also leave a comment if you'd like me to talk about another topic. Thank you.